Well, I didn't introduce myself. I'm Mark Rivers. I was at Brookhaven from 1983 to 1993 working on the microprobe beamline X26 at the old NSLS. Although I wasn't a Brookhaven person, I've always worked for the University of Chicago, so we were a partner in that PRT. 93, I went to the APS, and which didn't exist at that point, but it was being built, and we were building beamlines, and and the APS had decided to use EPICS as the control system. It was developed primarily by two guys. You know Bob D'Alessio, or people who were here up to a couple of years ago would know Bob, and Marty Kramer, who was at the APS. Bob had been at Los Alamos at that point. And together they put together this EPICS control system based upon a previous one that was written at Los Alamos that was called the GTAX, is that right? Anyway, it was at the ground test facility. And so I learned EPICS early on. Marty taught a class on it, and then I've been working on mostly like drivers for things we need at beamlines since then, and the infrastructure to support that kind of software. So this is, and I want to keep this very informal and sort of you guide what it is you want to know about. What I've prepared are talks on ASIN, and I'll explain what that is for people who don't know. Today and this afternoon, basically covering ASIN. Actually, I forgot that this afternoon there's also going to be a talk brief about motor, writing motor drive, how the motor software is organized. And then the plan, and then tomorrow morning I'll give a talk about area detector, which heavily uses ASIN. And then we'll have time this afternoon and tomorrow and Friday to sort of do hands-on stuff if you guys have specific things you want to look at, problems you're having, questions, and so on. Now I know a number of you are new, relatively new to EPICS. Oh, I should say here that all the talks, or at least all of today's talks now, are available online at this URL, both in PowerPoint and PDF. I'll give you if you want to follow that link or write it down, give you a second. So it's Cars U Chicago EDU Data Rivers NSLS2 ASIN class. Yeah. So, and please, questions anytime, interruptions are welcome, because I don't know. I want to be careful that I'm not going too fast, so that I'm talking about things that you don't understand. So please be sure to ask questions if I'm getting ahead of where you are. You got it? And when I'm done with tomorrow's talks tonight, I'll have to update them a little bit. Then I'll put them there as well. But right now, it's only the talks for today that are at that location. So because a number of you are new or relatively new to EPICS, I thought I'd just also, and now you can get these links in this talk on the link I just gave you, to just mention what some of the most important documentation for EPICS is. The most important by far, the most important is the EPICS Application Developer's Guide. This link, of course, is for a particular version of that document. It gets updated with each release of EPICS. And this is sort of the Bible that, the reference guide for how the EPICS IOC, the database, and so on. There's a link I forgot to put in here, which you can get from this page, which is also the channel access reference manual. This is the record reference manual that describes all of the different fields in the EPICS records. This link is the documentation for ASIN, the stuff I'm going to be talking about today, and you can also get to it. In fact, most of these you can get to from their source code. So if you go to this one, this is the master branch in GitHub. And one of the things I've done, if you've ever looked at this document, is that I've now put in links to all of the level 3 headings in here. So it's easier to navigate this document now because you can go to all the subheadings, which you can't in the version that's currently at the APS. Then there are, and I don't know if you have looked at these, but there's a series of EPICS training videos that were put together in probably a couple of dozen classes that were given at the APS in 2014 and 2015. And those are available. So those are available. This is the web page that link will take you to. And these are the lectures from 2015. And you can get both the PDF of the PowerPoint here, and then there are YouTube videos. So if you're interested in learning about these things, and some of these are what I'm going to be talking about today, basically updated versions of these talks. But there's lots of other lectures here, and this is the 2015. There's also an equivalent page for 2014, which has a more introduction to EPICS. So if you haven't looked at these and you're at the level where these would be useful, it's a good thing to know about. And then finally, these are the links for the documentation for the state notation language, which is a very useful piece of software for sort of coordinating software in the IOC, basically doing channel access, puts and gets, but having that running inside, potentially at least inside the IOC, rather than as, for instance, a Python client. And then this is the documentation for area detector and the documentation for stream device. Of course, there's much more, but I would say this is some of the most important documentation you need if you're going to be writing drivers or support for hardware. The first talk this morning is about ASIN, the sort of introduction or overview of ASIN. And so, but before I jump into that, I'm going to say, what's my philosophy about how to deal with a new device? Somebody brings you a new device and says, I need this to run on the beamline or the accelerator. In general, I would say if the device uses strings to communicate and it's not too complex, use stream device. Stream device is very easy to use. You don't have to write any C code or C++ code. You just have to write this protocol file in a database, and you can control the output and input from the device. And it's not limited to ASCII. It can also be used to read and write binary. The main disadvantage of it is that it's difficult to deal with a complex device where the parameters interact. And effectively, you need to have some state information about the device, to know what mode it's in. Am I allowed to send this command, or do I have to send this command? If it gets to that level of complexity, stream device is probably not the best thing to use. So you should probably go to writing a real ASIN port driver at that point. Or if it doesn't use strings at all, there's no option to use stream device. Even stream device, it's useful to know about ASIN because at the low level, it is using ASIN. It always uses ASIN for the low level communications, be it serial port, TCP/IP, or GPIB. So it helps to understand ASIN even if you're just using stream device. Okay, so if the device doesn't use strings or it's complex, then write an asyn port driver, and preferably using the asyn port driver C++ base class that I'm going to talk about in the talk after this one, later this morning. Very important, if you use asyn, you should not need to write device support for any of the standard records. And I think this is a good thing to do, or I should say to not do, because writing device support, in my view, is difficult, because you have to understand not only the device, you have to understand the record. And so that makes it more difficult. And writing device support is constraining to the developer because you've decided what records you're going to support. If you write an asyn driver, then the developer, the IOC developer, can choose what records to use to communicate with it, or indeed not to use records at all, because these drivers, asyn port drivers, can be called from other software. They could be called directly from a state program or even another control system. Okay, so what is asyn and why do we need it? It's useful to think about the architecture of an EPICS IOC, which I think is probably familiar to most of you. So you've got at the top level you've got channel access, monitors going out channel access, the channel access doing puts and gets to the EPICS database with the database access routines to the IOC database. At this level, the interfaces are very well defined in EPICS. Between the IOC database to the record support, that is also very well defined. Between the record support and the device support, the interface is pretty well defined. There's a set of functions that a record expects device support to provide. Initialize, report, write or do the I/O, that kind of thing. So this is quite well defined. The problem is that the next level down, the interface between device support and a device driver, is very poorly defined in EPICS base. There is a set of there's a function table that a device is supposed to provide, but it has two functions, initialize and report. So it has no standard definition of how you actually do the I/O between device support and a device driver, which means that, and this is the niche that asyn is filling, is to make well-defined interfaces between device support and device drivers. Because what was happening before that was everybody was writing their own device support and their own way of communicating between the device support and the driver, which meant that, for instance, it wasn't possible to write generic device support, device support for the AO record that would work with any driver. You couldn't do that because this interface wasn't defined. And so you needed custom device support for each driver. So asyn provides standard interfaces between the device support and the device drivers, and as you'll see, it provides a lot more. But that was the initial motivation for working on asyn, for developing asyn. So a little bit of the history. Why is it called asyn? So asyn replaces some earlier packages that had been used at the APS. One was called Hideos, and one was called MPF, Message Passing Facility. And those had a number of limitations. So back, I don't even remember how long ago this was now, but what? Marty decided that we needed to replace those and started to develop asyn. So his initial concept of asyn was limited to asynchronous devices. In other words, slow devices, where in EPICS, when a record is processing, it must not block. The record processing and calling device support must happen as quickly as possible. So you cannot wait for any communications with a slow device. So that means that the driver that you're using for that needs to run in its own thread, and EPICS needs to basically start an I/O operation and then get notified when the I/O operation completes. So that was his basic goal for writing ASIN. So it provided the thread per port and queuing that you need to do that. But I started using it soon as he was developing it and realized that it would also be really nice if we could use the same interfaces for synchronous devices, things that are fast where you don't need this blocking. So that's what currently in ASIN, we're not limited to these asynchronous devices. It supports synchronous devices, but we're stuck with the name, right? It's going to always be called ASIN because it would be way too much work to change it, even though it's totally not the right name anymore. Okay, one thing to realize about ASIN is that it's really independent of EPICS, except for the optional device support and the ASIN record. These things have to work in an EPICS IOC. Because at the low level, it's only using libcom from EPICS base, which is what gives you OS independence for things like threads and mutexes and events and so on. So you can use ASIN in code that doesn't run in an IOC. For example, ASIN drivers could be used with Tango or another control system. We also use this now a lot for unit testing because you can instantiate an EPICS driver outside of the context of an IOC and test it, right? Just with standard C++ code without running an IOC. And we do that for the plugins and area detector. There's not nearly as much unit testing in EPICS as there should be, but this provides you a way to do it. Hey. Libcom is the first thing that gets built when you build EPICS base, and it provides, for those who are not familiar with EPICS but are familiar with C++, it's kind of like Boost, right? So it gives you OS-independent ways of doing these things: threads, mutexes, events, linked lists. It defines stuff that even for networking, instead of opening a socket with a socket call, you can do EPICS socket create, and that hides the fact that Windows and Linux and VxWorks do it differently, right? So it's an OS-independent layer for.
It's specifically EPICS.
No, it's specifically EPICS in that it comes with EPICS base, but there's nothing about an IOC in it, right?
The package itself was kind of put together for EPICS.
Exactly, it was put together for EPICS. It is. All the names have EPICS something in them, right? The function names, but it's. It could even be packaged independent of EPICS base. It isn't, but it could be. But there's a flag you can set now when you build ASIN that says EPICS libcom only. And when you do that, if you build ASIN that way, the only dependency on EPICS base will be libcom. It doesn't depend on the IOCs at all. Yeah.
Bit of a confusion. So the ASIN, the original one was for non-block, right?
For blocking.
For blocking.
Yeah, blocking means you need to be asynchronous.
Okay.
Right. Does that answer your question?
Yeah.
Okay. Yeah, basically for slow devices.
Okay.
Yeah.
So now that is both synchronous and asynchronous, so it's basically covering everything, right? Nothing is neither
That's right.
synchronous. And
Yeah, I have not come across any driver that I couldn't write using ASIN. And in fact, all the drivers that I had previously written that didn't use ASIN, I've converted so that they do use ASIN. Yeah. And sometimes you have to think about whether a driver should be synchronous or asynchronous. What's slow, right? Is it 100 microseconds? Is it a millisecond? Is it 100 microseconds, but if something's wrong, it might take a second? So then, in general, there's not a big penalty for just saying it's asynchronous, right? And making it so that it runs in its own thread. There's a little bit of overhead, right? There's more task switching involved if it's an asynchronous driver, because you go from whatever is processing the record has to queue a transaction, and then some other thread gets the message and wakes up and does the work, and then goes back. So there's some task switching when you do asynchronous processing. But in fact, that overhead is pretty small on modern computers. Okay, so this is the overall architecture of EPICS. So you have something up here which you could call the client. I'm sorry, this is the architecture of ASYN. You have an ASYN client, which is typically device support, but it doesn't have to be. It could be state notation language, code. It often is another driver. So you can have one driver, let's say area detector has a driver, but it's talking to an underlying TCP/IP driver, which is in turn talking to the device. Right? So you can have layers of ASYN drivers. Or this could be non-EPIC software altogether. And in ASYN, you have an object called a port. And this is the object that's responsible for communicating with a particular piece of hardware. And so you write a port driver here, and it can talk to, in some cases, multiple devices. For instance, let's say it was an ADC, and it's a 16-channel ADC. You would have one port driver for the ADC, but then multiple addresses within that driver to talk to channel 0, channel 1, channel 2, so on. And then the client talks to the port over interfaces, which have names, and they're essentially pure virtual functions, right? It just says these are the methods that this object has to implement for 32-bit integers or 64-bit floats or strings. And those interfaces, there's one, and I'm going to get into this more, that's called ASYN common. All ports must implement ASYN common, and it basically implements connection management and reporting. That's all that interface does. So sometimes, connection management means, connecting the port to the device. In some cases, that's really meaningful, and it has some operation behind it. Like if it's a TCP/IP driver, that would be create a socket, destroy a socket, right? Connect or disconnect. With a serial port, there's not much to do. You can't really connect. Sometimes, at least, you can't connect and disconnect from a serial port. So that's ASYN common, and then you have a number of other interfaces. ASYN octet, which is for reading and writing. You could call them strings, but it's not necessarily ASCII data. It could be binary data, but a sequence of octets, bytes. Then there's an int32 interface, and there's a number of other interfaces that I'll get into in a minute. So that's basically the structure. So the client needs to open an interface to the port and then communicate with it over that interface. And this is how the control flow works for a slow device, an asynchronous device. So the step one here is the record. Let's say somebody does a CA put, right? So now the record is going to process. It calls device support. Device support recognizes that this is a slow device because it can ask the port, are you a fast device or are you a slow device? Can you block or not? If it can block, then it calls ASYN manager, which is the sort of set of routines that are globally available for working with ASYN. It calls ASYN manager queue request and asks ASYN manager to queue a request to communicate with the underlying port driver. At that point, ASYN manager puts it on a queue. Well, at this point, the record the device support sets packed in the record. Packed means processing is active, and the record support immediately returns. I haven't shown that on here. But as soon as it discovers it's a slow device, it calls queue request, sets packed true, and returns. So the IOC can continue processing, right? It's not blocking the record from processing. Now, in the ASIN manager has a queue of requests that are going to that port. When the one that was just queued becomes ready to run, because the other ones are in front of it are done, it calls back a function in your device support that says, okay, that you now have control of this port and you're able to do the I/O. So this is the callback function in the record device support is now doing the low-level I/O to the driver. So it can be doing write and read operations directly without having to worry about blocking because it's running in its own thread. And it has exclusive access to that port. That's guaranteed. So it can do I/O operations without having to worry about, without having to take mutexes and so on. It's got exclusive access to that port. When it's done, it then asks EPICS to process the record again. So now the EPICS will come in, process the record. When the record processes and sees that packed is true, it says, oh, I'm in the middle of an I/O operation. I've started an I/O operation, but now I have to actually go get the data. So now it calls device support again, which also recognizes that packed is true, has cached the I/O. So whatever I/O it did here, it's cached in device support, and now the record comes back and says, please finish processing. It copies the data into the val field, for instance, of the record, and then says, I'm done. All right. So, yeah, that's how the flow control works for a slow device. You don't need to worry too much about this. What's actually happening in record device support, it's helpful to learn, but in my view, this is all written, right? In other words, we've already written this device support for all of the EPICS records. So what you only need to worry about is this box right here, what the low-level driver does. But you need to understand how this works. And every once in a while, we go in and fix this or improve it. This is what happens with a synchronous driver, a fast device. So again, somebody does a CA put to the record goes to device support. Device support says, this is a fast device. It still calls queue request. So it calls queue request, but ASIN manager says, this is a fast device. I don't need to actually start, queue this for another thread. It just immediately calls your callback routine. So you still write the device support the same way with a callback routine that gets called. It's just that it's going to be called now in the same thread that's processing the record. So it immediately gets called. It immediately does the I/O, which has got to be fast, and then it says, I'm done. So the only real difference is that device support here doesn't set packed and return. It calls queue request without setting packed and does the I/O. So the nice thing is that it makes it so the device support hardly does anything differently for slow devices and fast devices. It's making almost exactly the same calls to ASIN manager.
So the programmer decides what is fast and what is slow.
That's right. When you create this driver, you set a flag in your initialization that says, I'm fast or I'm slow. And if you decide later that you want to change that, you change one bit, and all the rest happens for you behind the scenes. You don't have to worry about anything else.
Does the device support of the ASIN manager ever dynamically decide to switch between the two depending on
No.
maybe the last time it was on slows or...
No, it doesn't look at that. And there are some limitations here because it's either fast or slow. Now, for some devices, certain operations would be fast and certain operations would be slow. But if any operation can be slow, you have to say it can block. It doesn't have that level of granularity. Okay, so these are the methods in asyn manager that a driver needs to know about and call. So the first thing is a driver has to register the port. So it basically, and every port, every asyn port has a name, right? You just give it it's a string name, has to be unique in that IOC. So you give it these flags for, is it multi-device? In other words, does it support multiple addresses? Can it block? And is it auto-connect? So an asyn port, asyn can automatically try to connect to the device every time that there's any I/O if you set that flag. If you don't set that flag, then the user has to manually call the connect method, right? Usually you use auto-connect. But there might be some times when you want to disable that. And you can do that dynamically. That this is sort of the initial state when the port is created, but you can change if it's auto-connect or not at runtime. And then if can block was true, then asyn manager will create the thread that in which the I/O in that port is going to be done. Then you have to go through, and for each interface that your driver is going to support, you have to register that interface, and basically giving it a pointer to where those functions are, right? And so you must always register asyn common, and then depending on what your driver does, you might register asyn octet, asyn int32, asyn float64, asyn 8 int 8 array. There's a whole bunch of interfaces there, and you have to register each one. And then you can also say, does my driver support doing callbacks on the int32 interface? In other words, I might call back device support asynchronously because some new value has changed. And this says, yes, I might call back on the int32 interface, and so on. If you do an interrupt, a callback, you call a function called interrupt start and interrupt end. Asyn has a concept of interpose interfaces. What this means is that, let's say you've got a driver that supports asyn octet, like the TCP/IP driver, right? The TCP/IP driver itself, for instance, doesn't support the end of string processing. Oh, I think that's fine. What we have is an interface that goes in between, so that's called the EOS interpose interface. That looks. So if you've told it, my device is going to terminate each message to me with carriage return line feed, and don't return to me until you see a carriage return line feed. Even if you get a few characters before that, don't return until you've got a complete message, and strip off the carriage return line feed. That's not done in the TCP driver. That's done in a driver that interposes itself between the client and the underlying driver. So that same end of string processing module is used for serial ports and TCP ports and GPIB ports and so on. And there are a few of these. For instance, with Modbus. Modbus is a communication protocol used with PLCs, and there's sort of an underlying message. And then, depending on whether you're using serial, ASCII, serial binary, or TCP, there's some header stuff that you have to put at the beginning of a message and a checksum at the end. So the driver is written to only package the message, and there's an interpose interface that looks and say, okay, what's the other garbage I need to put at the beginning and at the end, and strip off on response. So interpose interfaces are useful, but they're fairly rare. Okay, so this is an example for a synchronous driver on the int32 interface that can do callbacks. So the driver defines the interface type. That's a typo. That shouldn't be int32 array. It should be just int32. Let me just turn this off. unplug it? Pull the cord? Okay. So it basically defines the interface here, registers the port with the name, registers the common interface, registers the int32 interface, and then registers an interrupt source, meaning it's saying I can do callbacks on the int32 interface to device support. Callbacks, I should say here, would be used usually with input records that have scan equals IO interrupt. So in other words, you have an input record that you don't want to constantly be polling the driver to say, what's the new value, what's the new value. The driver will call device support every time there's a new value, and if the record has scan equals IO interrupt, the record will then process. But typically the driver would only do that callback when there's a new value, right? So basically means you don't have to poll. You get the input records update automatically whenever there's a new value, which is generally what you want. Okay, so that was how, a simple way of how a port driver would set up. For clients, what you do is you create a structure called an ASIN user, and I'll explain what that is in a minute. You connect that structure to the port, to the device. Then you find each of the interfaces that you want to communicate over with find interface. Then you say, I would like to register for callbacks on one or more of these interfaces. You can query the driver characteristics. In other words, can it block? Is it multi-device? Is it enabled? So on. And then finally, you can queue a request for I/O to the port. So ASIN Manager will call you back when the port is free. It'll call you back instantly if it's a synchronous driver. It'll call you back whenever it's free, whenever there's nothing else in the queue. If it's an asynchronous port, and it'll call you on a different thread if it's an asynchronous port. And then the client does these I/O calls directly to the interface methods in the driver. For instance, it calls ASIN octet interface write or read. So here's some example code. So this would be for a long out record. And this is the link field that defines how to access the device. So the syntax is at ASIN, then the name of the port, which the port registered with when it was created, the address, which would be 0 if it's not a multi-device, or it could be 0 through n. If it's a multi-device, you can give it a timeout. How long should it wait if something goes wrong? And then this string here at the end identifies which parameter is it that you're talking to in the driver. So the driver might have multiple int32 parameters that it controls. So for instance, if this was a DAC, a digital to analog converter that we're writing to, there might be the value, the actual DAC value, but there might be another parameter which is the gain, right? And so this would define which parameter it is that you're talking to. And I'll explain more about that as we go on. So the client calls create ASIN user, creates one of those ASIN user objects, which I'm going to show you what it is. Then it calls parse link. So there's a utility routine that will take this string and parse it for you and return to you the name of the port, the address, and this string, the user parameter. So then you connect device with the port name that you just got out of there and the address. You figure out, can it block? So this will tell you, will return a flag here that says, can it block or not? Then it looks for the interface, int32, and then finally calls queue request. And here, when we created the ASIN user, we associated that ASIN user with a callback function. So this is the address of a function in your code here that will be called when queue request is ready. So whether or not it's a fast or slow driver, this function is what will actually do the I/O when you call queue request. So when you call queue request, this process callback will now, this function in your device support will be called, and it will actually call the int32 read function, passing it the asyn user and getting back a value here. Is that clear? Okay. So this is what this asyn user structure looks like. And you really do need to know a little bit just to understand this. So every time, so this is the structure that is the fundamental, I call handle, that's used by asyn. So you create one of these with create is asyn user, or you can take an existing one and duplicate it. There's asyn manager functions to create them and duplicate them. And this structure contains, this is the part of this structure that's visible to the user. There's a hidden part of this structure that's used by asyn manager that keeps track of, what port is this connected to, what address, and so on. But the part that's user accessible is here. So there's an error message that a driver, so if you call the driver and you get an error, it'll put the error message in this part of the structure, and the size of the error message. A timeout, this is where you can set the timeout for a particular I/O operation. There's some some pointers for user private in usage here. And then there's a pointer that the driver can use. These I would say are rarely, if ever, used, but they could be. They're there for future reasons. This integer here, reason, is essentially what says which parameter is this. Is it the gain or is it the data? So data might be reason 0 and gain might be reason 1. A timestamp, which is the time that the driver can set this timestamp. And if you do something in your EPICS database, you can make it that the timestamp associated with the record is the one that the driver provided and not the time that the record actually processed. So it's a way to set precise timestamps. So you might want to say, when I collected this image with area detector, I want the timestamps for all the records associated with that image to be exactly the time the image was collected, not the time each of those records processed. And then there's some auxiliary status fields here. Status, an alarm status, and an alarm severity that the driver can set so that the record will go into alarm, will know the correct alarm state based upon whatever happened with the driver. Right? So it's a way for the driver to communicate alarm information back to the caller. Okay. Oh, sorry. Yeah. This one?
Yeah. So the timeout is set in the CMD file and propagated down or no? Who sets the time? Who sets the timeout?
This timeout, yes, this timeout with standard device support, it would be in that field here. So device, you give it a timeout here, and if you're using the standard asyn device support, that sets this timeout.
Okay.
Right. But if you were directly doing something, directly calling a driver, not through standard device support, you would have to manually set the timeout here.
Okay.
Go ahead.
Another question is, where the device timestamp is being information how on the device level, but how it gets propagated into...
Okay, so in every record in EPICS has a field that says where does it get its timestamp, right? If you set it to so every time the standard device support, every time it processes, it copies this timestamp value into the timestamp field of the record. That will be replaced by the time the record actually processed unless you set the flag in the record that says use the device timestamp. I forget what that field is called, right?
Yeah, so this structure is shared with the driver, and even the driver fills all this field.
The driver fills in some of these fields are filled in by the driver. These would be filled in by the client. No, this is filled in by the driver. Yeah, you're right. Go ahead.
All right, so pretty much driver fills it, and then everything comes in out.
Yeah,
Okay.
that's right. That's right. And so this is, even if the driver didn't set the timestamp, it'll be copied to the record. But if you didn't set the field that says use the driver timestamp, then it'll be replaced. So even if this is garbage, it's irrelevant. But if you set that flag, you better be sure your driver is setting the timestamp correctly. Okay, so these are the standard interfaces that are defined in the asyn package. So I already mentioned asyn common, which just has report, connect, and disconnect. These are the I/O interfaces, and most drivers implement one or more of these interfaces. And each of these interfaces have a write method, a read method, a register interrupt user method, and a cancel interrupt user method. Register interrupt user is the thing that says, call me back. No, it says I can do interrupts. Okay, so then asyn octet, as I said, that's the thing for sending strings or streams of 8-bit bytes. In addition to write, read, blah, 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 it has a flush method, a set input EOS end of string method, set output end of string, get input end of string, get output end of string. Asyn int32 has one additional method, get bounds. So this is a way for device support to say, is this a 12-bit device? Is this a 16-bit device? And for converting from integer units to floating point units in an analog input record, it needs to know that. Then there are integer array interfaces for 8, 16, and 32 bits. There's something called asyn uint32, so unsigned int32 digital. This is intended for binary devices, right, where you're going to write a set of bits and read a set of bits. And it has some additional, well, first of all, when you do a write, you pass not only the value, but a mask, which says which bits are going to be affected by this write or read operation. And then it has a thing to say which bits can generate interrupts, those methods. There's a float 64 that doesn't have any additional methods. And then there's 32 and 64-bit array interfaces, a generic pointer interface. And this interface is used for when the thing that you need to pass to the driver is more complicated than these data structures, right? So you use this for simple data structures, integers, strings, numeric arrays. Anything more complicated, you use this. And the driver and the device support have to agree on what the heck is it a pointer to, right? So area detector uses this to pass. The pointer is to an object called an ND array, an n-dimensional array. And in the motor driver, this passes to a structure that's motor driver specific. And then finally, there's an asyn enum interface. Enums in EPICS are the menus, right? An MBBO or an MBBI record. And here is where the driver can define what the choices are. Let's say you've written a driver that communicates with a particular series of detectors. But each detector is a little bit different. And, what are the choices for the shutter type? Or what are the choices for this? The driver, instead of having to hard code into your database the MBBO or MBBI choices, the driver can define those choices because it goes out and says, oh, this is model A, so these are the choices. This is model B, it's a different set of choices. This can even be done at runtime. So if you change from 8-bit to 16-bit mode, then your choices for the speed might be different. So this could be updated at change from 8 to 16-bit mode, and now your speed choices would change. And then there's a few. It must have a battery. Maybe did we also disconnect the telephone? Yeah, it's completely untethered. There you go. I'm sure there's a way to turn it off, but it wasn't obvious. Okay. So there's some miscellaneous interfaces. One is called set option and get option. This is a way to pass key value pairs. So this is used in the serial port driver to pass like baud rate, start bits, stop bits. So it's two strings basically, a key and a value. They're both strings. On GPIB, there's stuff that's GPIB specific in that interface. And then there's something called driv user, which I'll get into in a second, which has a create and a free method. You're free to create new interfaces. In other words, these are just the interfaces that come with ASIN. If you had a particular driver you need to write that needs a new interface, you can do it. In practice, I don't think any drivers that I know of do this, right? And everything is using these standard interfaces because for the ones that you can't do with the simple data structures, if you just use this, it takes care of everything else. So there's a structure that you can, if you write a driver using the C code rather than the C++ code that I'm going to talk about later this morning, there's a lot of busy work because you have to register the port, you have to register every interface, you have to register can that interface do interrupts or not. For every one of those calls you make, you got to check the status return and print an appropriate message. And it turns out you get a lot of pages of busy work. So the first thing I did for writing a C driver was to simplify that, basically build a structure where you just you just set the fields in this structure and say go. And it does all that work of registering the port, registering the interfaces, registering whether they can do interrupts or not. So you basically, so you give it a pointer to each of your interfaces and a flag that says it can interrupt or not. This is an example of a real driver without using the standard interface header, the structure that I just described. So this is like the first page of code. The next page of code is you're filling in all these structures in these interfaces you defined. Then you're calling, it's not even here, I think, registering the port. Anyway, so you have to call register interface or initialize, depends, different ones are done differently. Register and interrupt source, initialize, register interrupt source, error checking, blah, blah, blah. It ends up being, I think this is like 6 or 7 pages of code just to get going in your driver with busy work. So if you do it with this ASIN standard interfaces structure, you basically just fill in some pointers here, set some flags as to which of the interfaces can interrupt, and then call this one function. Even this, you'll see in the next talk, is more work than you need to do. Because if you use the ASIN port driver C++ interface, all of this is done for you behind your back. So you don't have to do even anything this complicated. Okay, this driv user interface is important. This is the thing that that takes this string at the end of your link and turns it into that ASIN user reason field, the reason field in the ASIN structure. So the driver parses this link, finds the driv user interface, and then basically does whatever it's going to do with that. There's two things it could do. Almost all cases, in fact, every case I know about, it just sets the asyn user reason field. But there is another pointer there where it could do something more complicated, like it could set a function that's called for this, different functions that are called for these different user info fields here at the end. But in general, it just sets pasyn user reason. What exactly it does is completely transparent to the client. All you do is call this function to pass that string to driv user create, and it will modify your asyn user structure in some way that should be hidden to you. Right? The client doesn't know about that. Okay, let's talk about support for callbacks, which I've mentioned now briefly. So these are, you could also call them interrupts. So all of these standard interfaces support callback methods for interrupts. And as I said previously, these are usually used for input records that have scan equals IO interrupt, so that the record will update its value asynchronously whenever the driver tells it. So the client says register interrupt user, gives it a callback function, a pointer to some private data, and then the driver will call that function anytime there's a change in that parameter. The good thing is that if you're working in a real-time operating system like RTEMS or VxWorks, this callback won't be at interrupt level, so you can be guaranteed that you can do anything you want. If you're writing interrupt level code in a real-time operating system, you usually can't do things like call printf, at interrupt level. There's restrictions on what you can do at interrupt level, but you don't have to worry about them. So these callbacks can be used by device support, other drivers, and so on. So there's lots of examples in the area detector, in the struct multi-channel scaler, and then in some measurement computing devices that we're going to learn about this afternoon. Look at. So, for instance, this is an IP330. This is an ADC, right? It's a VME ADC, and so this is the interrupt function that's actually called by VxWorks or RTEMS that is running at interrupt level. So we don't want this code to be doing the callbacks to asyn device support, because that would be at interrupt level, and that's not a good thing. So what this does is it's reading out all 16 registers from this ADC, packing them into a message, and then sending an EPICS message queue try send. So it takes the data and does an EPICS message queue try send can be called at interrupt level. If it fails because the message queue is full, for example, it will just return immediately with an error. Then this is a thread that is running in the driver that's calling EPICS message queue receive in a loop. So it waits, it blocks here until the interrupt routine sends it a message. Now it takes the data in that message and loops through doing the interrupt. So it calls asyn manager interrupt start and gets the address of the next client. So multiple clients could have registered for callbacks on this port. So it's going through and looping over all of the clients and basically calling them back. So this is calling back this thing, the P32 interrupt callback is calling back the callback function for all of the device support, whoever's registered for callbacks here. And loop. This is a linked list of client addresses, essentially, and then calls interrupt end. Again, I'm just showing you this because I think it's good to know how it works. It turns out that if you use asyn port driver, you don't need to worry about this. You make one call that says, please do the callbacks. And does this. And not only does it for the int32 interface, but for all the interfaces. It looks and says, oh, has anything changed for float64? And if so, it does all the float64 callbacks and all the octet callbacks. But it's good to have some idea what's going on under the hood. Okay, let's just talk a little bit about performance. So, this stuff can be very fast. This is that ADC driver was digitizing 16 channels at a kilohertz, which means it's generating real VME interrupts at a kilohertz, and each interrupt results in 16 callbacks to the int32 device support for analog input records, and one callback of an array of values to an MCA record, and one float callback for fast feedback. So it's doing 18,000 callbacks a second, and on a pretty low performing PowerPC CPU in the VME crate, that's only using about 21% of the CPU. So it's pretty efficient. Okay, so as I mentioned, one of the real advantages of ASIN is that it provides a very nice set of generic device support so that you should not need to write any device support. You only need to write the driver support. The record support comes with EPICS base. The device support comes with ASIN. Only the driver needs to be implemented. So new hardware can be supported by just writing a driver. And so you've already seen an example of this. So you say, in your database, you say the device type is ASIN int32, for example, and the input field is this, where you give it the name of the port, the address, and the timeout, and then some string that identifies what parameter it is that this particular record is connected to. So on the int32 interface, there's support for the AI, analog input, analog output, binary input, multi-bit binary output, multi-bit binary input. These are like menus, long out and long in. There's a device support called ASIN int32 average, which is, let's say you have an ADC that's doing callbacks at a kilohertz. You don't want the record to process at a kilohertz. You'd like it to average all the readings it gets, and then the record is processing at, let's say, 10 hertz. Right? And so that's what this device support does. This is the uint32 digital, so it's intended for bit I/O, and that again has binary output, binary input, MBBO, MBBI, records called MBBO direct and MBBI direct, long out and long in. Float64, so this would be analog input or output records where you're directly writing a floating point value instead of an integer value to an ADC or from an ADC or to a DAC. Octet, which is so there's support for the string in record and the string out record. The limitation of these is that they're limited to 40 characters, right? And that's not going to go away. That's a channel access limitation. But then there's support for waveform records, and waveform records can be used to read and write strings of any length. And so they're used a lot, for instance, in area detector. A lot of times we're using waveform records so we can have file names that are longer than 40 characters, whatever. There's support for all the arrays, 8, 16, 32-bit integers, 32 and 64-bit floats, for the waveform records, both in and out. And the enum interface supports these, BO, BI, MBBI, MBBO. So now all of the Synapse modules that I'm responsible for now all use this standard ASIN device support. There's no specialized device support at all. So this includes the area detector, Modbus, DXP, which are digital signal processing stuff from XIA, the IP330 ADCs, Unidig, Quad EM. So this is a number of these quad electrometers, including 2 that Peter Siddons has designed here. Those all use this type of support. Industry Pack DACs, the measurement computing that I'm going to talk about later, Canberra multi-channel analyzer, the Struck multi-channel analyzer, and now a lot of the stuff in motor, which I'll talk about this afternoon, uses this standard ASIN device support as well. Now, the ASIN device support that comes, the standard device support that comes with ASIN is only for the records that are in EPICS base. And there's a few records that we're using and you guys are using that are not in EPICS base. So that includes the multi-channel analyzer record, the scalar record, and the motor record. So, but what I've done there is, again, I've written it to be device independent. So there's a single device support file for the motor record that works with any motor driver. There's a single device support file for the scalar record that works with any scalar. And the same with the multi-channel analyzer. One nice thing about this is that because they use the standard ASIN interfaces, these drivers, in principle, they're not limited to these records. In other words, I can control the motor velocity from an AO record or from the motor record. Right? So because I can just hook up my AO record to talk through the standard ASIN device support to the driver, it won't completely work with the motor because the motor record has some state logic in it, right? So I could set the velocity and I could tell it to go, but it wouldn't do the backlash correction, because that's being done in the motor record. But one thing that we should be thinking about for the future is, does that kind of logic really belong in the record, or does it belong in some base class of the motor driver, so that the motor driver implements that logic, not the record, and then you can get rid of the motor record and just use standard EPICS base records to control a motor. That's what we're doing with area detector, right? With area detector, there's no specialized records being used. It's all the standard records in EPICS base. But you need to move the logic that's currently embedded in the motor record down to a different layer. This is just an example of what the generic device support for IP330. And we can skip this. Okay, and you got a few things about the more details about the generic device support. One is ring buffers. So now let's say your driver is you've got a digital input module, right? That's reading the state of a TTL level. And the TTL level is low, it goes high, and then it goes low again. And so your driver's going to do two callbacks, one on the 0 to 1 transition and one on the 1 to 0 transition. But let's say, and if the pulse is 100 milliseconds wide, that's not a problem, right? You're going to get two callbacks. The record's going to process twice. The binary input record's going to go from 0 to 1 on this transition, going to process, and then back to 0 on this transition. But what if the pulse is only 5 microseconds wide? The problem is that the binary input record can't process fast enough. And so if you get two callbacks in rapid succession, the record's only going to process once. And it only has time to process once. It's going to miss the second transition. Or it's going to only see the second transition because it's going to get a callback. It's going to say, please process. By the time the record processes, the second callback will have happened, and so it's going to only get the value actually that it already had, right? The 0 value. It's going to miss the 0 to 1 transition. So what we've worked around that problem by having input records have a ring buffer. So if it's getting callbacks in rapid succession, it buffers them in the device support and then asks the record to process. The first time it pulls out the first value, the next time it pulls out the next value. So you will see all the values up to the size of the ring buffer. And the default ring buffer size for most records is 10. So you could get 10 rapid callbacks and not lose any of those transitions. You can change the size of that buffer by adding, and I don't know if you guys are familiar with what are called info tags. So in your database, you've got field this, field that. If you also add this that says info, and you use this string, asyn : FIFO, and you set that to 20, that would increase the size of that ring buffer for this particular record to be 20 instead of 10. Also, string in, string out, and waveform records default to they don't buffer, because that could be a lot of data, right? It could be kilobytes of data, and you'd have to have multiple multiple values of that. So the default on those is 0, that they don't do any ring buffering. But if you set this field, you can tell them to do ring buffering as well, even for string out, and waveform records.
To some extent, it's part of the record itself, or you're adding that field to the record.
It's called a tag, and so there's a way for device support to ask, does this record have this tag? So the record doesn't really know about it, but it's passed down, it's available to device support. So the standard ASIN device support now looks for these tags and behaves accordingly. Not the driver, device support. The driver doesn't know about the ring buffer. The driver just does callbacks. And then whenever it wants to do a callback, it does a callback. And device support decides whether to put those into a ring buffer, and if so, how big it is.
And device support is in the level of ASIN. So it is all in the ASIN.
Yes, I'm talking about the standard ASIN device support. The device support for all the records in EPICS base.
And the ring buffer is used by default. So
The ring buffer is used by default on all records except string in, string out, and waveform. Yes. And the reason I did this was for exactly what the thing that I just described, where I had a pulse that I was missing one of the edges, and for some applications you really can't miss an edge, right? Because you need to know that it went high and it went low. You're not going to get the time right. In other words, the timestamps of those EPICS records are not going to reflect exactly when it went high and low, because it takes some time for the record to process. The records probably take, it depends, but maybe 50 microseconds or something to process, maybe even less. But there will be certain times that it won't be able to keep up.
But even if you get the timestamp from the driver,
You could. No, if you got the timestamp from the driver, then it would at least be more accurate, right? Yeah, it would be whatever the interrupt latency on the system is that you would get that. Any other questions? Okay, let's take a break. When do you want?